Hello and welcome back to week 4 of the policy process class. This week we're going to cover the themes from chapters 9 to 11 of Calling Bullshit. It's a few less chapters to read, and also this will be a shorter video than normal, in part because, as a reminder, you have a paper about the book and your policy area that you're choosing to work on due at the end of this week. More details of that can be found on Canvas, and I'll also post about it in Slack. So let's start with conditional probability, because this is a pretty foundational concept that we should spend some time with. So you can think of probability in general as how likely something is to happen. Does it happen half the time, 25% of the time, 90% of the time, etc.? You can see this in all sorts of, prominently sports will predict the probability of winning or losing games or certain things happening. But this sort of notion of probability can be applied to other things, elections, or even just like policy implementation and the odds of something happening when something else happens. Which brings us to our next area, which is conditional probability. That's how likely something is to happen given that something else has already happened. How likely am I to carry an umbrella given that it's raining outside? Obviously more likely than if it wasn't raining outside, right? Unless you're someone who just carries umbrellas 24/7. But for most of us, we're more likely to carry an umbrella if it's already raining. And so this is the foundation of we observe one thing and it changes how likely we think something else is to happen. So probability of being a fan of UK sports might be 1% if we know nothing about someone. But if we know they went to UK, then that probability is much higher. I mean, they might not like sports at all. They might have grown up being a fan of some other team and never adopted UK despite going there. Not everyone who goes to UK is a UK sports fan, but a higher percentage of the people who go to UK are UK sports fans than of the general population out of everyone, right? So p-values have become fairly key to science and the social sciences as well, of which I take public policy to be a subset or combination. We're drawing from political science, economics, sociology, psychology, etc. And the thing is, p-values are telling us the probability of observing a set of data conditioned on a hypothesis. So what is the probability that we see the data we see given a certain hypothesis? Now the problem is, the thing we normally want to talk about is the probability of our hypothesis given the data. So note that the notation here, probability D, vertical line H, is probability of D happening given H has already happened. And you can see that this is reversed. And the problem is, when we're being casual about our language, we tend to take evidence that is actually about the probability of the data given the hypothesis and try to apply it and make statements about how likely it is that our hypothesis is true given the data. And this is wrong. The probability of the data given the hypothesis is not the same as the probability of the hypothesis given the data. This is at the root of a lot of scientific communication problems. There's a link to a 538 article talking about how this trips up practicing scientists. And further confusing the issue, I'll note, is that the hypothesis in question here is usually the null hypothesis. How likely is it that there's not some sort of difference? But we're generally interested in the alternative hypothesis. So what we have is the probability of the data given the null hypothesis, and yet what we want to talk about is the probability of the alternative hypothesis given the data. And if we're not extremely careful in our language, it's just really easy to slip back and forth and be talking about one thing with our words and another thing with our actual evidence. Okay, so I'm going to be upfront about this in terms of p-values as proof by contradiction. This may or may not be helpful. This may depend on if you've studied traditional logic at all. If this is not a helpful way for you to think about p-values, then ignore it. But if it is helpful, well, then hopefully it's useful. It makes a lot of sense to me in terms of how we should think about p-values. I'll also say I haven't seen it a lot elsewhere in terms of a way to think about p-values. So while this is, correct, it maybe is just not that helpful and therefore not that widespread, but, give it a shot. So traditional proof by contradiction holds something like, if we are interested in disproving A, we might go ahead and hypothesize that A is true and show that if A is true, we can logically deduce that B must not be true. But in the real world, B is true. This is a contradiction. You can't have contradictions within a logical system. So if our logical system leads us to say both B and not B, then the starting assumptions must be wrong. And our starting assumption was A is true. Therefore, A must not be true, right? If A leads to a contradiction within a formal logical system, then A can't be true. And that's how proof by contradiction works in formal logic. And I think there's a similarity in statistical logic where we say, if our starting hypothesis, usually the null hypothesis, is true, then our observed data is highly unlikely. So we don't have this whole like, B is not true, full stop. But what we're actually doing with our evidence is saying, D, our data, is highly unlikely. But we actually observed it, right? And this is a contradiction. Not as strong as like a formal logical contradiction, but it's a probabilistic contradiction. If our starting hypothesis is true, we really shouldn't be seeing this. And therefore our starting hypothesis is unlikely to be true, right? The other thing to say here is like, this only makes sense to me in some context. Like if we're testing two different barrel designs for distilling whiskey, it makes sense to assume they might offer the same yield. And if we observe data that's unlikely to occur if that initial assumption is true, we can say that, well, they probably have different yields. And we might care a lot about that, right? We might want to pick the one with higher yield. But the experiment, using a p-value, doing the null hypothesis, all of this to me, it can make a lot of sense within this experimental context. And that's part of why it's a popular design for all of its flaws, right? There are some contexts in which it's a very powerful way to actually talk about the data we observe and make concrete decisions like, which barrel design should I use if I want a higher yield on my whiskey, right? On the other hand, if we're, say, trying to find the price elasticity of whiskey, doesn't make a lot of sense. We're pretty sure that this is not, in fact, zero and that lower prices sell more, right? We have a lot of evidence about this from other fields. We have a lot of evidence of this from within whiskey and other whiskeys and brands and so forth, right? So, like, the p-value is answering a question that no one is really asking. Like, how likely is it that price has no effect on how much we sell? Well, yeah, no, obviously price has some effect. The question is more like, how well can we identify that fact? So we care about the point estimate we get here, which is like the number. We might say, we think elasticity is -2. And we care about the confidence intervals, plus or minus 1. We think it's somewhere between -1 and -3, right? As you raise the price, sales go down. So we do care about this, and we care about these confidence, but the precise things about p-values doesn't really make a ton of sense to apply in this context. And if we were to find, because we didn't have much data, say that, actually our confidence intervals included 0, which is another way of in most contexts, saying like, our p-value is not significant. Would we then go to our sales team and say, hey, good news, price has no effect on what we sell. Raise price as high as you want. Like, hopefully, that's kind of ridiculous. The problem was we didn't have enough data to show that price made a difference. And our conclusion was that price therefore doesn't make a difference. And that doesn't follow. Our conclusion should have been, we need a better experimental design, we need more data, etc. And if you draw this sort of wrong conclusion, it can have real world consequences, right? Price of whiskey doesn't matter that much, but like, there are medical studies that do in fact suffer from these same sorts of problems. And of course, policy decisions are often made based on studies that can suffer from these same sorts of problems, where the answer should have been not, it doesn't make a difference, but we still don't know. We don't have enough evidence. We can't tell, right? I will say, like, it's an unpopular answer, but a lot of the time the correct answer for any given set of data or study or observation is like, well, it makes us marginally more confident in this, maybe, but the truth is we don't know. And it's hard to convey that well. And frequently we probably should just say, we don't know a lot more than we actually do. Okay, I have less to say about the final 2 chapters. I think they're mostly good advice in terms of how to spot bullshit. Definitely question the source of the information. In an ideal world, I think I've talked about this before, yes, you would go through and you would look at all of the information for yourself and do your own assessment. In reality, knowing where it comes from gives you helpful information, and it's not realistic to think that you're going to be able to sort through everything. If you already know it's an unreliable source, simply don't trust it. Alternatively, if you know it's a reliable source, trust it a bit more. Not absolutely. I'm not suggesting that, just because it's from a reliable source means it's true. Just because it's peer reviewed does not mean it's true. Just because it was in a reputable paper or journal or magazine does not in fact mean it's true. But it's less likely to be bullshit. There is some degree of filtering that goes on with all of those processes. That means that for the most part, the reason they're reputable sources is they filter out and don't publish bullshit. That doesn't mean they filter out everything or they're never wrong. But, they're less likely to be publishing that sort of nonsense information than non-reputable sources. Be aware of unfair comparisons. And then this is a big one, especially for the modern era and social media spread. If it seems too good to be true or too bad to be true, it probably is. And watch out for confirmation bias here as well. Like, if it seems too good to be true to you, if it lines up with everything you've already believed and you're like, oh yes, this is the perfect example or the perfect piece of evidence, there is at least some chance that it is in fact wrong. Think in orders of magnitude. And this is to say just, roughly estimate how big the effect size actually should be. If someone is telling you that something moves a presidential election by 20 percentage points, that's fairly obviously wrong. Like, within a polarized environment, like, nothing has that sort of impact. Avoid confirmation bias. We just talked about this. And consider multiple hypotheses. So, think through what would it mean for this to be true? What else would it imply? What can we hypothesize? Do any of those actually hold up? And then refuting bullshit. This is, again, they're examples. Being memorable is, of course, just good communication advice. Counter examples are probably by far the easiest way. If you don't want to spend a lot of time going through thoroughly and the bullshit is of the sort that can be refuted by a single counterexample, that's probably the most powerful way. Providing analogies, redrawing figures, as we talked about with data visualization, and then trying your own sort of null model and seeing what actually happens there is another way to look into, or not just to look into whether or not something is bullshit, but after you've already determined this is bullshit, I should say something about it, how do I refute it? Actually go ahead and specify out, how this sort of model would work. Okay, these are discussion questions. I will post them in Slack as well. Good luck on your papers, everyone, and talk to you next week.